Hi, today we will see one more application of a diode, that is a clamper. So here in clamper we will see what is a clamper, how it works, and what is the circuit diagram of a clamper. We will see all these details of a clamper. Now first, what is a clamper? We want to know that what is a clamper. Mainly the clamper is a circuit. Mainly a clamper is a circuit which shifts the signals from different DC level, introduces a DC level, introduce DC level to AC signal. Mainly the clamper work is introduce a DC level to AC signals. In some conditions we want to introduce some DC signals to AC signals. Like these clampers are used in television receivers to control the video signals. That's why we are using these clampers mainly in televisions like TVs. So this clamping network shifts a signal to a different DC level and introduce some DC level to AC signal. Mainly this is the purpose of a clamper. And now we will see what is the circuit diagram of a clamper. What elements are there in a clamper? Here we draw one resistor and one diode, capacitor, diode and resistor. This is our circuit diagram. This is VI and this is the V naught. This is the capacitor, diode and resistor. This is the circuit diagram of a clamper. So what is this? A clamping network has capacitor, diode and resistor. Means here capacitor is occurred and one more resistor is occurred. That means here have time constant. How we denote time constant is in tau. So tau is equal to RC, resistor and capacitor. So the time constant of a tau circuit must be large. So the voltage across capacitor does not discharge suddenly when diode is not connecting. We know in a circuit diagram, means in a AC waveform, fundamental AC waveform, what we are drawing here, this is the input signal, right? We know this. So this waveform significantly, one time diode is conduct and one time diode is not conducting. That time here capacitor is charging and discharging in some conditions. So it's not discharging, means it is capacitor is some charge is storing. The main purpose of capacitor is the storing of some charging. In that time the output of a short circuit V naught is 0. So here we have some Kirchhoff's law, that is at the diode conducts resistor, at resistor some V is there and at capacitor some V will occur and V naught at the time it will be 0. So we will see the Kirchhoff's law. What it is minus V and at minus V naught. So what we are doing, sum of voltages is equal to 0. So 0 means minus 2V minus V naught is equal to 0. Therefore V naught is equal to minus 2V. That means this total signal will be 2 times. Output signal will be 2 times jump to the clamp towards the downside. Means like this it will appear. Total input signal jumps towards the output signal. This is the main clamper circuit. Here we see the portion of input signal forward bias is the diode. When diode is in short circuit condition, the capacitor is charges up to a level. That time the diode, the voltage across the capacitor is equivalent to the open circuit state. During that condition, it assumed that capacitor will hold on some charge. So capacitor hold some charge in this condition. On that time, voltage will appear. So in clamped networks, the total swing of output is equal to the total swing of input. It is a basic clamper circuit. So next we will see one more application of a diode, that is a main application mostly we are using nowadays, that's called as rectifier. What we are calling those are rectifiers. In these rectifiers, those are types of rectifiers are there: a half wave rectifier, full wave rectifier, and bridge rectifier. Rectifiers, three types of rectifiers are there. So what is a rectifier we will see, and what terms we are using in rectifiers we will see. All those details and full discussion about the rectifiers. Okay, now what is a rectifier? Rectifier is defined as electronic device converting AC voltage into unidirectional voltage. So it converts AC voltage to some unidirectional voltage. It converts some AC voltage to unidirectional voltage. So this unidirectional conduction device is our PN junction diode. Okay, these rectifiers are classified, we already told you: half wave rectifier, full wave rectifier, and bridge rectifier. So first one we saw the half wave rectifier. In case of half wave rectifier, we want here one circuit diagram of a rectifier. AC type unidirectional voltage. That's why for AC we are taking here one transformer. This is a basic structure of a half wave rectifier. In a half wave rectifier, we are taking a transformer, diode, and RL. Across RL, we are taking our output signal. So here it converts AC to pulsating DC. So first of all, what happened during the positive half cycle? Input signal of during the positive half cycle, here we are taking, we always know signal of it is a sinusoidal wave, AC. Maximum voltage is Vm, here Vi, this is minus Vm, right? 0, pi and 2 pi, this is a T. Now we want to see what is the output. So now during the positive half cycle, diode D is conducts, because input signal means plus positive is there na, so anode will be conducts. So diode D is conduct. That means here voltage drop is 0 up to pi. Half wave rectifier will be conducts, so half of the signal will appear up to pi. And again, during the negative half cycle, anode of the diode becomes negative. That's why here diode is not conducting. In this condition, diode impedance is infinity. That means here RL is 0. That in that case, this negative half cycle will disappear. So in half wave rectifier, half of the signal, means positive signal only appear at the output, and negative signal will be disappear. This is the half wave rectifier. Already in the name only it have a half wave rectifier. And these rectifiers we are using some factors, we are using some terms. Those are ripple factor, form factor, and peak inverse voltage, and transformer utilization factor, efficiency. We are seeing what are those. Okay, now we will see the first one, ripple factor. Here we will see. Okay, ripple factor. What is the ripple factor of a half wave rectifier? Ripple factor means ratio means we know ripple factor. Ratio of means RMS value of AC component and DC value of component. So RMS value of AC component and DC value component is ripple factor. And after that ripple factor, one more term we are using, that is called efficiency. Efficiency is we denoted by now, and this DC output power by AC input power. Because rectifier output is DC, input is AC, that's why output power by input power is efficiency. And next we are using another term, peak inverse voltage. Peak inverse voltage. What is a peak inverse voltage? It is defined like maximum reverse voltage. Remember that peak inverse, in the name only it have maximum reverse voltage, that diode without destroying the junction. Here peak inverse voltage of a diode is maximum voltage, because in a negative half cycle, and in the negative half cycle diode will be peak inverse. It's the same, it not increase or decrease, it will be 0. That's why peak inverse voltage is only Vm. Here we have now only Vm. That's why peak inverse voltage is Vm. And another one factor, transformer utilization factor. In AC circuit, actually we are taking here transformer na, so transformer compulsory having some utilization factor. How we define and how to calculate this transformer utilization factor is DC power delivered by AC rating of a transformer. Every transformer have some rating, so DC delivered, how much DC is delivered by AC rating of a transformer. This is called transformer utilization factor. And one more term we are using, form factor. Form factor is RMS value by average value of voltage. RMS value, what it have? Vm by 2, because half wave rectifier Vm by 2. In case of full wave rectifier, it has maximum voltage, means Vm, and average value Vm by pi. That means the average value form factor is pi by 2. It means 1.57 something form factor. And last term what we are using is peak factor. Peak factor is, in the name only it have peak value by RMS value. We know that peak value is Vm, and RMS value we know Vm by 2. That means 2 is the peak factor. So these terms we are using in a rectifiers: ripple factor, efficiency, peak inverse voltage, transformer utilization factor, form factor, and peak factor. So next we will see the topic of half wave rectifier and half wave rectifier already we saw, and next we will see those full wave rectifier and bridge rectifier. Full wave, full wave rectifier. Same in case of full wave rectifier, we have one circuit diagram. So here also AC, that means transformer, but here transformer is a center tap transformer. Full wave, we are taking two diodes, these two are connecting, and load is connected to the here. Center tap RL, D1, D2, VI, and here we are taking V0. Same as usual, we are taking a sinusoidal signal 0, pi, 2 pi, V, Vm, minus Vm. So what is our output? We will check. During the positive half cycle, half of the signal, diode D1 is conduct. Diode D1 becomes positive. In that same diode D2 will be does not conduct. So diode D1 positive, and the same diode D1 conduct. So load flows through D1 and voltage drop across RL equal to the input voltage. So what is the voltage here? VI is equal to the RL. That means in case of pi, voltage is up here like this. Same Vm, Vi is equal to the near RL, that means Vm. In a negative half cycle, anode D1 becomes negative and D2 is conductive. In the same case, voltage will appear, but it will appear on upside at 2 pi. This is the full wave rectifier. Here also same, we are using those terms only. Ripple factor, form factor, transformer utilization factor, all we are using. But here in this case, some constants we are changing, because in last half wave rectifier we saw that RMS value is Vm by 2, but here RMS value is Vm only. And the peak inverse voltage also it will be changed, and efficiency is increased compared to the half wave rectifier in this full wave rectifier. Next we will saw the another rectifier application, that's called as a bridge rectifier. Half wave rectifier and bridge rectifier almost same. Some small differences are there. Mainly here, half wave rectifier we are using center tap transformer, and a bridge rectifier we are using just a transformer only, not a center tap. But here changing of diodes, here number of diodes what we are using is increasing compared to half wave and full wave. Here we are using 4 diodes. Sorry, drawing is slow. So diode D1, D2, D3, D4. Here we are taking across the load RL. Across RL we are taking V0, and across the transformer we are taking the VI. This is the bridge rectifier. So in bridge rectifier, same waveform will be appear, sinusoidal waveform VI, 0, pi, 2 pi, so time t. So during the positive half cycle, what will happen we will see here. During the positive half cycle, input AC voltage, diode D1 and D3 will conduct. The time D2 and D4 will not conduct. Remember this. And the time the load resistance across the RL is same in a VI, that means positive half cycle will appear. In a negative half cycle, these two diodes will work, means in first case D1 and D3. Here D1, D D3. In a second negative half cycle, D2 and D4 will conduct, and D1, D3 is not conducting. So across the load, it is constant, means Vm. This is the V0. And efficiency is same compared to the half-wave rectifier. All are same, but we want to know what is the main difference between the half-wave rectifier and bridge rectifier. Why we choose a half-wave rectifier and why we choose bridge rectifier. In some cases, here only we are using 2 diodes extra, but in case of peak inverse voltage, this bridge rectifier is low compared to full wave rectifier. So for this purpose, mainly for peak inverse voltage, we are using this bridge rectifier. So bridge rectifier have all are same bulk. And one more thing, here we are using general transformer, right? In case of full wave rectifier, we are using center tapped transformer. That also one more burden. That's why mainly we are using bridge rectifier in almost all works. And bridge rectifier only disadvantage is here diodes more we are using, means 2 diodes compared to in full wave rectifier we are using. Here 4 diodes we are using. Of course, in markets compared to transformer, diodes are cheap. That's why we are using this bridge wave rectifier. This is about the applications of a diode, clippers, clampers and rectifiers. In next class, we will see the topic of what is the problems in rectifiers, how we solve in competitive exams like GATE, PSU exams and SSC, IES, how they are giving about topics. We will see the topics, rectifier problems, how we solve. We will see the next class. Thank you. If you understand this topic, please like and subscribe my channel and press bell icon for further notifications.